thanks to Patrick for the introduction also to the SCENIC project. So I'll take advantage of the last few sentences that he mentioned before to introduce the concept of the SCENIC project in my own presentation. There is quite a few people that are to be mentioned and thanked for the results of this project. This is a European project that is actually coming to a conclusion. Actually, this very December is going to be the last month of activities, and it's part of the Future and Emerging Technology funding scheme. And as you probably know, the Future and Emerging Technology program within the 7th framework program of the European Community is aimed at funding projects that have a certain vision towards the future. So these are an emerging technology that might not see the light in terms of technological implementation in the immediate tomorrow, or maybe the day after tomorrow. But some of the things that you're going to see also in the demos, in the demo room, in room A, are actually some initial testing and implementations and prototypes that are somehow a side result of the theoretical results that have been developed within this project. As you see, the partners of the project are, in addition to the Politecnico di Milano, who's the coordinator of the project, there is the University of Erlangen-Nuremberg, and Imperial College, here represented by Patrick, and the Fondazione Bruno Kessler in Trento. And so let me just tell you a few things about what we have done in this project. And well, first of all, a few words about the market. And I have a few pictures of some products that have recently come up, at least in the past decade. They show some of the changes that have been brought into the consumer market by space-time processing, especially as far as rendering is concerned. Actually, line arrays have been in use for quite a long time, and we have representation from the industry that in this very room where they have been using space-time, a certain degree of space-time processing for public address systems, but also in the houses of in the households of people. You can actually finally see some of the things like sound bars that are actually based on speaker arrays, or systems that are able to diffuse sound using some wavefield synthesis principles, and so on. And so it's kind of interesting to see that the market is actually turning the attention towards this sort of products. One of the things that normally comes in the way to developing products that are in fact able to exploit space-time processing at best is really the environment. And in fact, one of the problems that the SCENIC project has tried to tackle and address has been to make the best out of the environment. So rather than withstanding the impact of the environment to space-time processing solution, the idea is to try to bring the environment into the picture, into the design, and make it work towards the end of achieving good rendering, achieving good sensing, and so on. So how can this be done? Well, the idea is to build some awareness, and the awareness can be seen in two directions. The first one that you see there in the top branch concerns in figuring out information about the system, the rendering system or the sensing system. So that's what we call self-awareness. And this includes operations of self-calibration. These are things that are starting to appear also in commercial products, although in a different sense, in a different direction. So the system tries to understand where, how it is located in space, and how the various components, speakers or microphones, are placed with respect to each other. Once you build this self-awareness, what you try to build is also some environment awareness, meaning that you try to figure out what all the walls are, the acoustic reflectors are in the environment. And then you have to bring them into the picture and make them become part of your design somehow. Can this be done automatically? Can this be done systematically in the design of an acoustic system? Well, we tried to answer this question in the SCENIC project, and we realized very soon that in order to achieve these results, we had to incorporate a bunch of broad technologies. Let me just tell you some of the things that are coming into the picture. Definitely there is global modeling and local modeling. Global modeling meaning that you try to model the whole wave field, or at least a description of the whole wave field. Local modeling means that you try to understand what the acoustic channel is between two specific points in space. Let's take a look at the global modeling first. One approach, and you will see something, is something that was already discussed partly by Patrick in the previous presentation, consists of modeling the whole wave field, the whole acoustic wave field, using techniques that are based on spatial sampling of the acoustic wave field and then spatial extrapolation of the wave field in order to figure out what happens in between the sensors. But there is also a different approach that consists of modeling, instead of the whole wave field and the equations that describe the wave field, you try to model the propagation of the wavefront in the environment. The idea here is, close relative to the idea of ray tracing or beam tracing, in the sense that you try to track the motion of the wavefronts into the environment and figure out how they interact with the environment, so how they bounce off the walls and this sort of things. So the representation in this case looks a lot more like a superposition of geometric layers, geometric beams that form the entire wave field at the end. This is another way of looking at things, but a different, yet different approach consists of not modeling at all the wave field, but still working on the global sense, meaning that you try to build some descriptors of the wave field. For example, some coherence maps, what we call the acoustic maps, the acoustic coherence maps. And they actually give you some information, some very precious information about the environment and the way acoustic beams propagate in the environment. But you don't have the exact wave field inside it. So this is what we call the wave field descriptors. And this is a useful approach that brought quite a few results within the project itself. Of course, we cannot ignore the classical approach to, which is a point-to-point approach, like a local modeling that consists of figuring out what the impulse responses are in a specific point when you produce the impulse in a different point. So when you have a starting point and the final point, you figure out the channel that goes from A to B. So that's a very important approach because that's what allows you to do quite a few things that are absolutely necessary for achieving the results within the SCENIC project. And I'll tell you in what sense in a minute. So let's begin with a little bit of some broad ideas on sound field modeling. The idea on sound field modeling is to focus on the equation, the wave equations, how the equation that governs the propagation inside the environment. You can do a lot of things with this. For example, well, of course, it's based on the idea of discretizing the equations in space and time. And this requires embedding the boundary condition. In our case, the boundary condition is the enclosure, the environment itself. And you need to embed it into the computational scheme of this wave equation. Then you have to find some model representation of the whole scheme. And then finally, you can perform, using this model representation, wave field interpolation and wave field extrapolation. So the idea is using these tools that are very powerful in space-time sampling processing, you can actually, starting from, for example, a closed line in space of microphones, you can extract the whole wave field around the closed line through a wave field extrapolation. There are many things you can do in terms of analysis there. You can, for example, study the geometry of the environment, figure out the geometry of the environment by looking at the shape and the interaction of the wave field with the boundary condition, with the environment itself. It's a very powerful analysis tool, but the reason why we use it only for specific things, but not for extracting information in the environment and making the environment come into the picture, is because it is still treated, the environment is still treated as a boundary condition. We would like to turn the environment from a boundary condition to a functional element of the design of the system itself. So we would like the environment to become one specific block of the construction of the system itself. So in this sense, geometric modeling is a little more explicit. If we think in terms of the propagation, we can track how a wavefront propagates inside the environment by looking at the way it bounces off any of the reflectors that are present in the environment. And if we track the motion of the wavefronts, we also notice that every time there is a reflector in the environment, the acoustic beam that is sent out by the source will split into many sub-beams depending on how many reflectors that are around. And this beam splitting process is basically an operation in which we track the visibility of the source that produced that kind of wave field. So this is it's kind of an interesting approach because it allows you to consider the way the boundary condition no longer as something to embed into equations, but it really becomes an element of the design of the system itself. And we use, in this approach, we use a lot of projected geometry. And the reason is, in projected geometry, it's something that was used also in computer vision. And it's very common to use projected geometry when you have cameras, like optical cameras, where you have an optical center where all the rays meet in one specific point. Now, in acoustics, obviously, the situation is only partially true because we don't have cameras in the traditional sense. But we do have points of accumulations of rays where all the rays meet. For example, microphones, we have listening points. And that also is a good way that allows you that suggests that using projected geometry could be a nice mathematical tools for our representation. But despite what tools we have been using, aside from the tools that we have been using, it's very important to underline the importance of learning what the environment shape is like. Because without that, we cannot exploit it, obviously. So how do we extract information on the environment? The goal will be to do so using acoustic methods. So we don't want to go there with yardstick and measure using that. We want to use the very tool that we are directing our technology towards, which is acoustics. So we want to send out acoustic signals and listen to what comes back. And using this information, we want to figure out where walls are and maybe how they are in terms of reflectance properties as well. So I'm going to tell you a few things about the geometric approach that we use in that sense. There are also other solutions. But if we normally start from acoustic measurements, and the acoustic measurements that we use are normally things like time of arrival, so which is basically the first echo that arrives. Also time differences of arrival. We have time of arrivals when we know the time of emission of the source. So if you're using a controlled source that is synchronized with the microphones, in that case we have time of arrival. But if we don't know when the source is producing the sound, for example, we go there and snap our fingers, we have no idea what the time of arrival is. So all we can say is when the time differences of arrival are between different microphones. In which case we use this type of measurement called TEOA. But we could also use compact arrays like a circular array or an eigenmic, something spherical, that gives you an idea of the direction of arrival. So depending on the type of sensor that we're using, we might have different types of measurement. Like I said, time of arrival, time difference of arrival, and direction of arrival. And these measurements could be associated to either a direct path from source to receiver, or even maybe a mediated path that goes from source to receiver by bouncing against a wall in between. So this could be an indirect measurement rather than a direct measurement that you have from a direct path. So what do we do with these measurements? We have to turn them into specific constraints, and these constraints must be combined together and studied in order to estimate the shape of the room itself. Once we have the shape, we can go beyond and perhaps estimate information on the reflection coefficient or the radiometric properties of the wall, how they actually reflect acoustic information. So we go in steps. We layer up our information with a certain progression. Let me just give you some ideas of a very broad idea. I will not go into formulas or anything like that, but I just wanted to tell you what kind of geometry pops up. For example, if you know that there is a source in this location here, and there is a receiver, the receiver is in the middle, the source is someplace else, you know how long it takes from the source to reach the receiver, because that you can measure using a TOA, time of arrival, time of flight. In that case, you know for sure that the source is bound to lie on a circle. It could be anywhere on the circle, right? So that circle has a nice description in projected geometry. It's a conic, basically. So it's a second-order equation. And that's okay. We won't go into the detail of that. But it's a specific type of equation that has a certain structure. Now, let's consider the situation where we have, again, TOAs, time of arrival, time of flight, and, but it bounces off a specific wall. In this case, the source is here, and the receiver is here. It has to bounce off a reflector before it reaches the receiver. We know the time of flight, the indirect time of flight, so it's like we know the length of this path, right? What kind of so basically the reflector must be the point of reflection must be a point of this ellipse, because if you have a string of a specific length, we can draw an ellipse using that kind of method. So we know that the reflector point must lie on an ellipse, which is again a second-order equation. It's again a conic, exactly like the previous one in terms of general shape, but it will be a different category of conic. So it will be an ellipse. Actually, there are interesting things that happen in projected geometry that allow you to describe this ellipse. Instead of an ellipse made of points, it's an ellipse made of tangent planes in this case. So you can actually estimate directly, you can write the constraint directly as a function of the reflector, which is kind of fun. It's not the only possibility. You might have, for example, time differences of arrival. And those of you who have ever seen methods based on time difference of arrival know that in this case the type of constraint that comes out is actually a hyperbola. So the set of points where the source is supposed to be given the time difference of arrival to two reflectors is actually another shape, which is a hyperbola. So it's again something that you can describe with a second-order equation, and so on and so on. You can have indirect paths. So the same type of constraint when it bounces off a wall takes on exactly the same shape. We can go on with DOAs, the direction of arrival on indirect paths. You find that there is another shape, which is the parabola. And so on. All the types of constraints that come out with this sort of measurements always take on the form of the shape of a second-order equation. It's kind of interesting because that allows you to combine things together into a global set of constraints that you can actually study simultaneously in order to estimate the location of the walls, in this case the geometry of the walls, or the location of the source, depending on what your unknowns are. So you can start from this constraint and shuffle the constraints up until you get to a specific problem to solve that is as a function of the things that you're looking for. For example, if we go from constraint to algorithms, you can define problems of self-awareness, so self-calibration of the system. You can define problems of source awareness, so you can figure out where the source is. You can figure out the radiance pattern. You can figure out you can extract the source in the presence of a relation, or you can work on environment awareness. So you can extract the information on the shape of the environment or the reflection estimation of the environment. All these things can be expressed as a combination of many constraints of various forms. In the geometrical case, all the constraints that we use have that specific form. Let me just show you a very quick video that shows a very, very simple application, the first one that we developed originally, where we show that we have two planar arrays made of just 5 microphones, nothing more than that. and we're producing a sound with a little speaker, and the acoustic images appear there, and the system automatically finds the location of the two arrays in space. So this is called self-calibration. It does that automatically. There are many other ways of doing that. This is just one simple example of application. So basically, you enter the room, you have two arrays of microphones. You have two, what we call the acoustic cameras, although it's kind of an incorrect term. But by producing noises, you can self-calibrate the system and know where the cameras are in space. But it doesn't have to be. Time of arrival. It can also be differences between time of arrival, which is actually a big step forward for us. For example, we want to deal with natural noises, not the noises produced by a speaker controlled by the same soundboard that controls the microphone. So we don't want to have synchronism. In that case, what we would like to do is to enter a room and produce some impulsive noises, and the system has to do some calibration, or perhaps to figure out where the walls are. So, for example, an application of this sort is based on the first figuring out the first echoes of the sounds that are acquired, then do the matching between the echoes in order to turn the time differences of arrival into times of arrival using traditional point-to-point channel estimation methods. And then once you have that kind of information, you can use the technique that I mentioned before based on the ellipses. So, for example, if you have microphones here and you have a source here, and as you move the source, every time you produce a sound in a different location, by snapping your hands, snapping your finger, whatever it is, you produce a new ellipse. So you basically, if you keep snapping your finger in the room, you'll see a demo there in room A. Every time you snap your finger, you will produce a new ellipse. And at the end, the walls will be found using some techniques that do this sort of selection and association, will be found as the tangent planes to all the ellipses around there. So you finally find your room by producing finger snaps. That's kind of a neat application that is based entirely on a geometrical approach. And the same thing can be done in 3D. In 3D, instead of having ellipses, you have ellipsoids, and you have to find the tangent planes to the ellipsoids. Some more things. The same situation can be done in the case of the DOA, the direction of arrival. This is the planar version of the eigenlight. It's actually a set of 8 microphones on a circle. And using this sort of planar eigenlight, you can obtain a bunch of parabolas in this case, and you find the walls as the tangent planes to the parabolas. And so on. The 3D version of that obviously will be an eigenlight, a 3D eigenlight. So where you have paraboloids and tangent planes to paraboloids. But how do we exploit the information of the environment at this point if you want to go beyond that? How do you, well, first of all, you have to think of the environment as a mirror. The environment is not just a place that produces unwanted echoes. You have to look at the walls as mirrors. And just like when you walk into a mirror room, you see yourself repeated many, many times around you. So you see your own eyes repeated many, many times. So you can see the room from different angles. But you can also produce light in different directions. So you can illuminate the room in different directions. Think of the same thing in terms of acoustics. Well, in that case, the arrays can be used along with their image arrays. So the mirror version on the wall. And therefore, this is a nice thing because, an eigenlight is not exactly a cheap thing to buy. It costs about 20,000 euros. And, being able to multiply it by a certain number of times thanks to the mirror is definitely something that comes in handy. Also, listening and rendering around the corner is a possibility. So you are multiplying, you're boosting the power of your system using the mirrors that are in the room. And if you do succeed in making sense of the reverberation, you actually get for free something that is a very desirable effect. reverberation in acquisition, and room compensation in sound rendering. Because at this point, whatever you get in terms of reverberation is no longer a bother for you. It's something that comes in, that is actually exploited to achieve the goal that you have. Meaning the reverberation is no longer treated as a reverberation, but it helps you in localizing sound, in the case of sensing, or it helps you rendering the sound in the case of speaker arrays. Let me just give you an example in the case of room compensation. Let's think of any type of array. For example, this is a type of array of speakers, spherical array of speakers. And this is the array that we have in the demo room, which is, it looks nice, but it actually is just a bunch of PC speakers, nothing more than PC speakers. So in the demo there, we'll show you something that works already with just very simple PC speakers. Anyway, whatever array of speakers you're using, the idea is to try to exploit the knowledge of the environment to control the reflection and make them help build the desired wavefields. So just to give you an idea, if you have speakers that form an array in a specific area in space, and this is the actual room that the speakers are, the same speaker will be reflected by the walls in an infinite number of locations in space. We only show the first order reflections here, but there are many more. Can we use, if we control the wave field that we produce inside here using this array, and we make also the image arrays through the visibility through the wall, contribute to the same wave field, all of a sudden, this is no longer a cause of reverberation, but it's something that helps building the wave field inside here. So we are actually performing reverberation. And this is actually a result of that shows the reverberation. These are the typical modal response of an environment that has reverberation, where you don't exploit the image arrays. If you exploit the image arrays, all the modal responses that you have here disappear, and it flattens out to a modal response like the one that you see below here, which is very close to the free field rendering. It gets much closer to the free field rendering. So it's like listening to the same array in open field without the room around you. And if you do have the ability to build some acoustic beams using the speaker array, then you can also do something more compared to that. For example, you can do wave field synthesis in principle with combined room compensation. You probably know that wave field synthesis, which is the acoustic holography that is now becoming a commercial product around. Commercial is a big word. I should say probably something that is available also in movie theaters, in specific movie theaters. There is a company in Germany called Iosono that builds wave field synthesis systems for theater installation and this sort of things. There are also other companies that are popping up that are working using techniques that are similar to ambisonics, and they're installing the first clusters of speakers into movie theaters around in Europe. But they're also relying on the fact that the environment that they're installing these things is actually a low reverberation environment. There is a lot of absorption on the part of the seats, on the part of the walls, and so on. So you don't have much reverberation there. So if you want to do wave field synthesis in an everyday environment, you have to deal with the reverberation. Not just deal, you have to exploit the reverberation. Otherwise, you will first need a bunch of speakers around you, like hundreds of speakers around you, which is a problem. The second is you want reverberation because you want it to work in your own living room, right? And you don't want to have speakers everywhere in the living room, otherwise our wives kill us. And the other thing is, it would be nice to be able to introduce a virtual environment in there. Can we do everything at once? Well, the idea is there. Now we're working on the first simulation. We have simulations. We are working on the first installations of that. You won't see a demo of this in the room, but you will see something that is halfway in that direction. For example, let's consider this is the real room. This is a real room. It's shaped like an L, for example. you have a real array inside the real room. These are the image arrays that come out of here. Obviously, they will not be completely visible because there is also occlusion on the part of the walls. So you have a bunch of partial images of this array. So these image arrays all contribute to the wave field inside the real room. So by considering them as real arrays, you are actually de-reverberating the room. Now you want to produce the same wave field that you would have if this array was in a different environment. If this wave field was to interact with a different environment. For example, this is shaped like a sort of a church. And so we can do beam tracing. You can trace the acoustic beams inside the church, which is you're tracing bundles of rays inside the environment. And we can do that actually quite efficiently because of the geometric techniques that I told you before, also in 3D. And this tracing allows you to account not just for the source in the environment, but also all the virtual sources with their visibility inside the virtual environment. And in fact, if you look at the wave field that comes out, once you render it, it shows clearly that there is a discontinuity here where the wings open up in the virtual environment. So this is something that opens the possibility to not just rendering a wave field into a real environment, but also to recreating a different environment inside the real environment that you have. So the real environment allows you to multiply the arrays and make them work towards the goal. The virtual environment is what you are actually rendering along with the source. And here's the type of wave field that you obtain in the discontinuity area, which is consistent with the theory. I think we're towards the end, so I'm just going to say one thing related to the wave field descriptors. With the wave field descriptors that I mentioned before, you can do very interesting things in terms of figuring out what the source is like. It's very important to know how a real source sounds in a real environment. So, for example, what you would like to have is the radial pattern of a real source as the source moves around. This is something that can be done with the help of the actual mirrors in the environment. So if you have, for example, an array of microphones in a real environment, you can actually infer the whole radial pattern of a source, like a speaker or a loudspeaker, whatever it is that is producing sound in the room, as if the room was anechoic, and as if the array of microphones were all around the source. So this is an interesting thing that you can do with the help of the environment. These are two examples of estimated radius patterns of different types of loudspeakers, which are based on these acoustic maps, coherence maps, knowing where all the walls are. So you can actually use the mirrors to see what the sound is like on the other side of the array. I think I'm beyond my time allowance, so I'm just going to wrap this up. What I try to tell you about today is how you can go about making the system work for you, the environment work for you, and boost up the performance of an acoustic array, whether it is a microphone array or a speaker array. But there is a lot more on the way that is still being developed, even if the project is coming to an end. We're all very excited because things are coming out, and there is never time to see them all. But for example, there are aspects of radiometric estimation, how to estimate the reflection coefficients of walls, how to use the visibility map in order to do the rendering without knowing or with an implicit knowledge of where the walls are. So instead of using explicit knowledge of the walls, you can use an implicit knowledge of the wall. And anyway, if you want to keep track of what's going on, this is the website of the project, and so I'm obviously available for questions also.